Okay, here we are, last section of the unit we're talking about. It's called linear and angular velocity. We're going to calculate linear and angular velocity provided information from a circular motion. So we're talking about circles and what happens on that circle. You have one linear motion, so like if you have a point, how is it traveling along the circle? That would be your linear motion. Okay, so the rate at which the rider changes position and distance per unit of time, so feet per second, miles per hour, radians per second, not radians per second, take that back. You got another way of looking at this is that if you have a central angle, how does this angle change in time? Like how quickly does that angle increase, or how long does it take for that angle to go around one revolution or whatnot? And that would be your angular velocity. So we got a Ferris wheel that has one trip around the wheel, 20 minutes. You could be talking about how fast they go because they're traveling around the circle, or how fast that angle changes. Now your angle velocity has a degree that looks like a degrees per second, radians per second, and sometimes it's called RPM, or a revolution per minute. All typical types of angular ones. Three formulas here. You got velocity equals the arc length divided by time. You got a new variable. It is a W looking thing. It is another Greek letter, but it talks about angular velocity. So you can get your velocity by taking the radius times the angular velocity. And the way you calculate out your angular velocity is if you have the central angle divided by some unit of time. Some things to note: that a radius is equal to 1 radian. And what I mean by radius is whatever the distance of the radius was on that particular circle. And that one rotation around the circle works out to be 2 pi radians. So what I'm going to do here is I'm going to take that one rotation in 20 minutes and convert that into an angular velocity based off of the degrees per minute. So I'll start off with one rotation over 20 minutes. And I know that one rotation in a circle in degrees is not 2 pi, it's 360 degrees. And if I cancel out the rotations, I'm left with 360 degrees divided by 20 minutes. Or if I reduce that down, I believe I've got 18 degrees per 1 minute. If I'm figuring out angular velocity in radians, though, it's still one rotation per 20 minutes. But now it's no longer 360, it's going to be 2 pi radians per 1 rotation. And while I'm at it, I'm going to take the minutes and convert it to seconds. And because I've got 1 minute is equal to 60 seconds, I'm going to put the 1 minute on my denominator, and I'll put the 60 seconds on the numerator, and watch how I got that flipped around, my bad. Got carried away. It should be 1 minute divided by 60 seconds. There we go. So now the minutes cancel out, and the rotations cancel out, and I'm left with 2 pi radians over 20 times 60, or 1,200. And if I were to calculate that with a calculator, that is about 0.0052 radians per second rather than minutes. Notice how radians was left on the numerator for my units and seconds was left on the denominator for my units. Okay, so a point on a circle is with a radius of 5 is hanging out on that circle. That dot is just going to cruise around that circle. It takes one rotation every 20 seconds. Find the linear velocity. Okay, because I'm given an angular velocity, and that angular velocity is then talking about the angle changing. The angle rotates one rotation per 20 seconds. By the way, because I've got angular velocity, I'm using that formula. So here is my, it's kind of backwards. I got my W I put first, times the radius. Now, Remember, radius is going to be in, one of my radiuses, 5 centimeter radiuses are going to be over 1 radian. So I need a way to get rotations and radians to kind of cancel out. So I'm also going to state that it takes 2 pi radians for 1 rotation. So now my rotations cancel out, my radians cancel out, and I'm left with, on the top of my fraction, centimeters for my unit and seconds at my unit. And if I go through and I multiply the 5 times 2 pi, I've got 10 pi over 20. Or if I calculate that out, 10 pi over 20, I get about 1.571 centimeters per second. A point moves around a circle at a rate of 60 revolutions per minute. Get that angular rotation or angular velocity in radians per minute. So I'm going to go with 60 rotations or revolutions. I guess they're synonymous, per 1 minute. And I'm going to say 2 pi radians per 1 rotation or revolution. Okay. Revolutions cancel out, and I multiply and get 120 pi radians per minute, or if I, again, use my calculator, I get about 376.99 radians per minute. A bicycle tire has a radius of 13 centimeters. Okay, so radius is 13 centimeters, and it turns at a rate of 3 radians per second. So again, I'm going with this one right here. So I'm going to take 3 radians. Maybe I'll do it in order again. I'll take the radius. Remember, that's 13 centimeters for the radius. Okay, for the angular velocity, but that's over 1 radian. Okay. So that when I multiply by the angular speed of 3 radians per 1 second, I cancel out the radians, and I'm left with 39 centimeters per 1 second. Now, to get the actual distance it travels, I'm actually going to use this formula, but I'm going to manipulate it a little bit. I'm going to get S by itself. S is my arc length. So S is actually a distance, and I'm going to take that V times that T. Now, my velocity from before was 39 centimeters per second, but my time's in minutes. So what I'm going to do here is I'm going to make it so that 60 seconds per 1 minute. I'm going to convert that into minutes, and then I'll multiply by my time of 1 minute over 1. And now my seconds will cancel out, my minutes will cancel out, and I'll take 39 times 60 to get 2,340 centimeters.